So now we're going to take a look at another transit type, and this is referred to as transit recovery voltage. And it's also going to be associated with capacitance, but instead of being associated with the large capacitance that we would see with power factor crushing capacitors, it's more associated with the stray capacitance that we would see, say, like in a substation. So this is a picture from some Siemens, a Siemens application note. And what it shows is it shows the basic use case scenario. And so very similar to what we had before with the fault, in that we've got a source model and we've got some type of a impedance in here. In this case, we're neglecting the resistance. We've got a circuit breaker, and then we have a fault that occurs. And what we looked at before for the first transit use case is we looked at the fault current. Okay, so again, we're going to have a fault current here, which I guess you can call the first transit. But now we're going to look at a follow-up transit, which is going to happen when that circuit breaker finally clears the fault. And usually that fault's going to be cleared pretty close to a current zero. And so what we see in this case is we see the system voltage, which is in the dashed lines. We see that fault current lagging by about 90 degrees. And then when the circuit breaker is operating, then what it's going to do is going to clear pretty close to a current zero. But when that circuit breaker opens up, we get a second event, which is going to be referred to as the transit recovery voltage. And what we see in this case is it starts from zero because basically that fault forced the voltage across this capacitance to zero. And what it's going to do is basically going to shoot up to a fairly high value, maybe as high as 2 times the source peak. And then it's going to ring, and it's going to ring at a much higher frequency than it rang during shunt capacitor switching transits, because the capacitance associated with this is not due to a power factor correction capacitor in the substation. It's actually due to the stray capacitance that we would naturally see either between metallic objects or when we have like insulators. And so if you go through the Siemens note and the references given on the bottom of the slide, what you'll see is you'll see the class of the breaker. In this case, these are 15 kV class breakers, so that's a very common class. And then what you'll see if we're at 100% interrupting current, that we have a situation where we can handle a transit recovery voltage as high as 25.7 if we're talking about metal clad switchgear, and 29.2 if we're talking about outdoor gear. Another interesting thing about this is a time to peaks giving. And the reason this is important is when we're talking about insulation on these circuit breakers and whether the circuit breaker is going to be able to withstand this transit recovery voltage, it's not just a function of the voltage magnitude, but it's also a function of the change in voltage with respect to time. All right. So insulation, if we put too much voltage across it, it will fail. If we also have a large change in voltage with respect to time across that insulation, it will also fail. And so what these ratings do that are in these types of tables right here is not only do they tell you what the absolute voltage would be for the rating, but it also gives you kind of a dV/dt value when it gives you this time to peak. So what I'm going to do is I'll break this lecture for this material into 3 different parts. First we'll go through the theory, then I'll go through a worked example, and this will be a pretty extensive worked example. And then I'll have a PS-CAD simulation associated with that. I'm just going to break that into 3 separate videos. So transit recovery voltage, we'll just abbreviate that a lot of times by TRV. And again, we're not only looking at amplitude, but we're looking at rate of rise of this voltage. We're looking at this value dV/dt. One thing that can happen if we're clearing a fault And if this stress on this breaker is too high, what we're going to get is what's called a restrike or reignition. What can happen is basically that insulation is going to fail, and what that circuit breaker basically going to look like is it's like it's closing again. So the fault's going to reignite. The worst case for this typically occurs if I have like a multiple pole circuit breaker when the first breaker is trying to interrupt the current. And so when we talk about this phenomena, we'll be talking about the recovery voltage. This is the voltage we're actually going to get across the terminals. This is kind of like the instantaneous value. We're going to be concerned about this peak, what's going to be that worst case stress. And then sometimes instead of talking about dVdt, we just simply use this term rate of rise of recovery voltage, or RRRV. And again, this is ratio whatever this peak value would be with respect to the time taken to reach that peak value. The scenario that we have for this, you saw this in the Siemens note, but this is just a different, this is my own drawing for this. Basically, this is the scenario. We start off by having the fault. We clear the fault with the circuit breaker, and what we're left with in this case is once we clear this fault, we're left with an LC circuit. If we had a little bit of resistance in here, it would also be an RLC circuit. But we're going to start, at least with the case, we just simply have L and C. We'll neglect the resistance for now. And again, this is straight capacitance, and we'll talk a little bit later where some of these numbers would come from. But when the fault clears, the fault's going to be typically clearing around a current zero or close to a current zero. And so in this particular situation, then what we're going to have for this fault, if it's a bolded fault, and what I mean by a bolded fault, it kind of looks like I have a piece of wire there out in the field. What that's going to do, it's going to pull this value of capacitor voltage pretty close to zero, essentially zero. And so what we'll have is we'll basically have a situation where we clear on a zero crossing, so the initial value of current through that inductor will be zero, and the initial value of voltage across that capacitor is going to be equal to zero. And again, what we're worried about is how high is this TRV value going to get? Is there going to be the possibility that that breaker insulation could fail and we'll get a fault current reignition? I wanted to say a few things before I get into the solution of the differential equations about the relationship between voltage and current, and why I'm not going to be working with a point on wave number when I do this like I did for the RL fault analysis. So let's suppose this is the form of the voltage, and we'll use a cosine form in this case, and theta would be a point on wave number that we could use if we're talking about looking at this analysis right here. We'll be assuming that stuff's occurring at time equals zero. In this particular case, if I have just simply inductance, and if I have a dead short circuit of zero impedance, then what I'm going to get is I'm going to get a steady state current where the peak of the current is going to be found by taking the peak of the voltage dividing through by omega times L. And then what we're going to have is we're going to have a minus 90 degree phase shift if we neglect the resistance in the circuit. What this is going to mean is that whenever I have a current zero, a natural current zero, that the peak source voltage is going to be at its maximum. Now, it could be that we get a voltage that's going to be its positive peak at a zero crossing, or it's going to be at its negative peak. But either way, it's going to be, the voltage is going to be typically around its peak value. And so what this would mean if we're looking at the practical cases that involve fault being cleared at a zero crossing, this point on wave is either going to be 0 or 180 degrees. And given that we're primarily interested in just getting a peak stress, we're not so concerned whether that's a positive or negative value, because generally these solutions tend to be kind of symmetrical. So we're just trying to get a peak stress, and this is why when I work this through, that I don't concern myself point on wave, because if I have basically an inductive circuit, basically I can just assume that the point on wave was actually equal to 0 or 180 degrees in this case. The other thing we got to factor into this right here is what's kind of going on when we clear the fault, and why am I basically saying this fault is going to be cleared to zero crossing. And this isn't a course on circuit breakers, but I just want to talk a little bit about what's going to be involved in this circuit breaker clearing this fault. So first of all, if we have a fault, what is actually the process of opening up that circuit breaker? Well, what we're going to have is we're going to have a relay here. And what this relay is going to be doing is going to be taking a measurement of the current going through the circuit breaker and making a decision whether to trip or not. So when it sees that current goes high, maybe it's an instantaneous overcurrent, maybe it's a time overcurrent type of a function which is going to operate. But what happens is that relay needs some time in order to know there's a short circuit, and then it needs some time to generate a signal and to send a trip signal to that circuit breaker. So there's going to be a delay of so many cycles in there, depending on what's the level of the current, whether it's a really high current or really low current. But anyway, there's going to be some processing delay. Eventually that circuit breaker is going to get that trip signal, right? So what we're going to have in that circuit breaker is we're going to have a couple of contacts, and there's going to be a mechanism which is going to be pulling these contacts apart. This is kind of a little simplistic, but this is basically what's going on. And so if we've got this in some type of medium, like say oil, let's say, or say this is a vacuum circuit breaker, then what's going to happen is we have a large amount of current that's flowing through these contacts right here. When I try to pull these contacts apart, what I'm going to get is I'm going to get some arcing. And what this means is when I start to pull the contacts apart, even though I don't have the mechanical connection anymore, I still have enough of an arc that current can actually still flow. And so it's not actually until the current, the fault current, goes to 0 or close to 0 that circuit breaker effectively isolates us from that fault, right? Now, one thing that can happen, this is especially something you could see with vacuum technology, vacuum breaker technology, is it may not wait until like a natural current 0. It's actually possible that that circuit could be interrupted when that current's pretty small, maybe some value like 5 amps or 10 amps or so. And that's what's referred to as a current chop. So what we're going to do first is we're going to take a look at initially what happens if I have the circuit breaker effectively isolated and followed a 0 crossing. But then later on what we'll do is we'll take a look at current chops, and we'll see kind of what effect current chops would have. And basically what we're going to see, if I have a lot of inductance in there, that could maybe cause some problems. So anyway, when you look at the circuit breaker model in PSCAD, this is why that circuit breaker has logic in there for current 0. This is why you generally have to have a little option you set about whether you want this fault actually to clear on a current 0 or you can allow for a chop. Because a lot of times what the default analysis would have in it would be basically assuming that the circuit breaker actually interrupts that, isolates that followed a natural current crossing. But anyway, if we're assuming in this initial case that we look at that we're assuming clearing at a 0 crossing of current, then basically that point on wave associated with this is going to be 0, 180 degrees. And so this is why in my analysis I don't have to have this value of theta, at least right now. So in coming up with the equations for this is going to be the form of the current source. Basically the point on wave is going to be 0 degrees in this case. And there's a lot of different ways you can set equations up. In this case, just to do something a little bit different, I'm going to go ahead and set this up using Kirchhoff current law. So if I look at this particular circuit, what I'm doing is once that circuit breaker is open, what I can do is I can look at the summation of the currents out of this particular bus, where I have the current going down through the capacitor and the current going off to the left toward the source. And so the way I can write this is the current going down through the capacitor C dVc dt. The current going through the inductor going off to the left is 1 over L times the integral from 0 to t of the capacitor voltage minus the source voltage. And then I have to add to that the initial condition for the inductor current, which is actually going off to the left in this case. But that's going to sum up equal to 0. So that's basically Kirchhoff's current law. And what I do is I take the derivative of both sides of this relationship here, and I divide through by C, and then I get this particular differential equation where I'm going to have the second derivative of the voltage plus 1 over LC times VC is equal to 1 over LC times V sub S. And what I can do then is I can substitute in for the form of the forcing function. Note in this particular case when I do this is that the circuit breaker is open, but the fault is still assumed to be there. So think about the fault as being zero resistance. All right. What does this mean? Well, what this means is what the circuit breaker sees is what the capacitor voltage is. All right. So the circuit breaker voltage is the same as the capacitor voltage. So this is why I'm concerned about the insulation breakdown. Because basically what I'm looking at is if this value of VC is high, then that's going to cause stress across that circuit breaker. So anyway, we're not directly calculating the voltage across the circuit breaker. It's assumed that's the same as the capacitor voltage. So when I want to solve this equation, I'm going to break this into two parts, just like I've done before. There's going to be a steady state part and there's going to be a transit part. The steady state part is what I can solve using phasors. And so basically I just have a voltage divider. The voltage across the capacitor in steady state is the capacitive impedance divided by the inductive impedance plus the capacitive impedance. This is times the source voltage magnitude at angle 0 degrees. What I can do is I can get some cancellation on the J terms in this coefficient here, and we see that eventually in the phasor domain, this is 1 over LC divided by 1 over LC minus omega squared times this phasor representation for the source voltage in this particular case. All right. So omega in this particular case is the 50 or 60 hertz fundamental. So if I substitute in, if I move this into the time domain, then this is the form of the equation, the time domain. So basically this coefficient is going to be a voltage divider. This is basically the source voltage. And what we're going to see in this case is that C is going to be very small. And this will actually cause just a little bit of a voltage rise. So in this case, the numerator is greater than the denominator. And this is going to give me just a very slight voltage rise, but not really too much, because that value of C is really kind of small. Now that I have the steady state part, then I can focus on calculating the transit part. And the transit part could be calculated by solving the homogeneous equation where the right-hand side of the quality is equal to 0. This is going to have a characteristic equation of the form S squared plus 1 over LC is equal to 0. And we'll have then a form of the solution where this transit part is going to be A1 cosine omega naught t plus A2 sine omega naught t, where omega naught is 1 over the square root of LC. If C small, it's going to be small, then what this means is that omega naught is going to be large. All right. So we're going to get a much higher ringing frequency in this case than we got with the power factor correction capacitor. So then when I add these two components together, this gives me the form of the total solution, and then I still need to solve for A1 and A2 using the method of undetermined coefficients. And so this is where I have to know the boundary conditions. And again, this boundary condition is going to be based on the no chopping scenario. So we're going to assume the fall clears at a zero crossing. So if the fault is cleared at a zero crossing, what this means is that the current going through that capacitor, this is going to be equal to zero right before and right after the switch associated with that circuit breaker operation opens up. You'll note in this particular circuit that, go back to this diagram, this is getting a little bit cluttered here, but basically once that circuit breaker opens, the current going through that capacitor is going to be the same as the current going through that inductor. So then go back to the boundary conditions. What this means is, since that inductor and capacitor are in series, the fact that the inductor current's equal to zero means that that capacitor current's being forced to zero right after the switching occurs as well. Note that we don't have any limitations on capacitor current changing instantaneously, but basically once that fault is cleared, then basically that initial capacitor current becomes the same as the inductor current. And we know that at time equals zero, that capacitor current is C dVt at time zero, right? And so if this current through the capacitor is equal to zero, then what this does is it means that this derivative of voltage for the capacitor at time zero is equal to zero as well, all right? So because of the inductor, that forces the boundary condition for the derivative of the capacitor voltage equal to zero, and that forces the boundary condition. Then we have, due to the fault, the boundary condition for the fault voltage is equal to zero. Now, again, if we perturb this ideal case, these boundary conditions change, and we'll see this in the worked example. But when we apply the initial conditions, then we take our formula solution, we look at time equals zero, and so basically, since this voltage is zero, we see that we have a way of calculating A1, because basically the A2 terms equal to zero, and then when I take the derivative of the voltage, what we're going to see is we're going to see this A1 cosine term go into a sine, so that's going to disappear, and then that A2 sine, when you take the derivative, that's going to give us an A2 omega naught times cosine, which evaluates to A2 omega naught at time equals zero. So anyway, basically if we apply these initial conditions at time equal to zero, basically what we're going to get is we're going to get these mechanisms for calculating A1 and A2. And so finally what we get is we get this particular form here. So it would be kind of useful for you guys to kind of do this on your own. You know, I left out a few steps in here, but basically by now you should know how to use the method of undetermined coefficients to get to this particular point. And what this is telling us is there's two parts of the solution. There's going to be a fundamental portion, say oscillating at 60 Hertz. There's going to be another portion that's going to be oscillating at a higher frequency, which is the resonant frequency of this LC circuit. We typically simplify this because omega naught's usually a lot higher than omega. So if we look at this coefficient, omega naught squared over omega naught squared minus omega squared, this is going to be pretty close to 1 if omega naught's pretty large. And something else we do too is we typically assume that since that high frequency portion of the solution is kind of what we're more interested in, we typically assume that for what we're going to be looking at, we can assume that that 60 Hertz source essentially looks like a DC value, that the 60 Hertz value doesn't really change that much. And so what we do is we basically assume that omega, if you want to think about it this way, is just equal to zero. That's what DC is. And then what this does is it gives us a much more simplified solution, that this capacitor voltage is square root of 2 Vm times 1 minus cosine omega naught t. What we can see from this is that we're going to get a peak value for this voltage when omega naught t is going to be equal to pi. So basically this, if you go back to the first slides I just showed you for this lecture, we saw when the fault was cleared that the voltage went from 0 to some really peak value. Basically this is the time that's associated with this, and that time is going to depend on what this natural frequency is. In other words, this time which this is going to happen is going to be pi divided by omega naught. So if omega naught's high, that's going to rocket up there pretty fast. It's going to be a high value dB dt. Now, where does this capacitance come from? Like I said, it's not power factor correction capacitor. Where this capacitance come from is anytime you've got two pieces of metal, if you have like a bus bar in the substation with respect to a ground reference, there's going to be an equivalent capacitance between that bus bar and ground. If we have any bushings, if we have like a piece of equipment and we've got some bushings out there, let's suppose, I guess a better example would be if I had some type of bushings with respect to ground, where we're going to connect up, like say bus bar here, and let's suppose this is grounded. So these bushings are just basically insulators. Basically there's going to be some equivalent capacitance across these bushings. If I have any type of transformer connected up, if I have a transformer, these transformers have equivalent capacitance in the windings, and so a lot of different elements have just some small amount of capacitance associated with them. And at 60 hertz, it really wouldn't factor into the 60 hertz solution. These would be so small. However, in this case, we need to factor this in because this is going to contribute to this transit recovery voltage. So there's a standard for ANSI market, IEEE standard 37.011, and I'm getting these out of the 2011 version. There's probably some updates in any more recent versions of the standard. What it does, it gives you tables for typical values as a function of the voltage level. And so if you had, bushings out there that are served as insulators, basically there's going to be a small amount of capacitance as shown in this table. For instrument transformers, there's a small amount of capacitance. If you have bus bars, there's a small amount of capacitance. And all these values may seem really small. I mean, we're talking about values here on the order of picofarads, right? Really small values. However, these values add up. These all add up in parallel. So if you talk about all the different possible sources of capacitance, you have to add them all up. And so just keep this in mind, that capacitors in parallel add. I'm not going to have you guys compute this stuff based on, say, like a substation layout, because this is a very complicated calculation. It's kind of like an advanced bookkeeping in a way. And a lot of times you're not going to get this accurately anyways. I mean, so you'll just have to kind of make some kind of guesses at what this could add up to. If you think about it in terms of looking at this effect right here, basically as you add more and more capacitance, what this is going to do is this is going to drop this frequency down. All right. So the more capacitance you can actually identify, possibly the less susceptible you're going to be to transit recovery voltage failures. But anyway, Don't worry about having to go to tables and get these particular values here, but just realize that there actually are calculation guides like the C37 standard, and I think they actually do in there walk through some examples of how you get all these different numbers for some practical cases. Circuit breakers, just the fact these have metal in them. Maybe they're in metal enclosures are going to have capacitance associated with them as well. So as far as trying to mitigate this, there's different sort of mitigation procedures. One mitigation procedure would be to have a circuit breaker which had what's called a pre-insertion resistor, and I talked about this a little bit before. But basically what you have in here is what's called an auxiliary circuit. And this auxiliary circuit has another switch with the resistor in. And this switch, this auxiliary switch, this would not be designed to handle fault current. It's just basically enough of a switch to put this resistance in and out of the circuit. And so what you would do is when you open up the circuit breaker, instead of just going to a scenario where that circuit breaker is the only thing in there, what you would actually do is you would actually put in this auxiliary resistor. All right, so you put this into the circuit a short period of time after the main breaker is open. What that does is it turns this into an RLC circuit, and it provides a measure of damping in here. The other thing you'll see in real life too is there actually be resistance out there. I mean, like there'll actually be some resistance in the source, and so in real life there's resistance out there which adds to the damping on the solution. So we wouldn't see the theoretical worst case, but it's hard sometimes to get a handle on exactly how much of that resistance is out there. So at least the worst case gives you a bounds on what could be going on. And so when we add that pre-insertion resistor into the circuit, basically what we have to do is we have to kind of add this into the formulation. If we assume that this fault still looks like a zero impedance, then basically that adds another leg into our Kirchhoff current law equation. And then we have to just factor into this equation the fact we've got current going through that resistance as well. And then this is what you have for the final solution, and then we're going to have complex roots, and that sinusoid, that high frequency sinusoid, is now going to decay out exponentially. So I'll work up an example on this in a second video where basically we'll have a substation with an impedance, and we'll start off by assuming the resistance is negligible. And this time I'll add a wrinkle in here where we have a fault resistance of 0.5 ohms, because in real life there's probably going to be a little bit of resistance in there. And so we'll see what kind of difference that makes in the solution. And then we'll also rework this with X to R ratio of 6, so we have some resistance in the source model. And then I'll go through an example that kind of shows what these waveforms will look like in PSCAD. I'm not going to spend a lot of time on this here, but what you see is we're going to model back-to-back transits. What we're going to do is we're going to start off with a fault current. And so we have the fault current in here. It's going to clear after a certain period of time. Remember, there's going to be a delay on how quickly the relay could recognize the fault. And when that circuit breaker, when the mechanical system can actually start to open up the contacts, you'll see in this particular case where we're closing pretty close to a current zero. And then this is the high frequency oscillation that's associated with the clearing the fault in this case. And of course, what we're adding in this particular case, if we're assuming that we've got some additional damping in the circuit, then we're going to be looking at scenarios where instead of this ringing forever, it's actually going to get damped out a little bit. But anyway, if we zoom in on the first couple cycles, and this is typically what we're interested in as far as looking at stress on the component, you could basically see that this does kind of look like this high frequency sinusoidal waveform. And what we're really interested in looking at is what is this number right here. And So this is what we're going to be focused on. This is it oscillating at a very high frequency, like 40 kilohertz in this case. But basically, what is this worst case magnitude of the voltage? Then how fast does that voltage change with respect to time? And this is what the hand solution is designed to give us. We don't really care as much of what happens way out here, but what's happening right here, that first half cycle of the natural frequency of this event, what's happening in terms of stress on the component. For references, I'll give you guys a link to Greenwood's text if you want to take a look at Greenwood's text. There's actually a wiki site on transit recovery voltage, and this Siemens reference is pretty good. And then if you ever wanted to look up, how you do this capacitive calculation, there's actually this standard, as the title suggests, basically it talks about how you analyze transit recovery voltage for AC circuit breakers. And so we'll just go ahead and end it here, and we'll take a look at an example then.